So, from last week, I wanted to make sure to get on the recording as well. There was an adjustment needed to be made to two of the formulas. We had them backwards. We talked about it on Friday. If you have these formulas backwards, it makes some of the problems really weird and have a tough time to get the right solution. So, I want to make sure to clarify. The angular speed formula is the one that contains omega. It's also the one that contains an angle in it. The angular speed formula has the angle in it, theta. The linear speed contains arc length, which makes sense because arc length is a distance, so it makes sense. One last thing I should mention. The formula V equals omega R. That formula is another one that's great to have. I used it a lot in the homework assignment, mainly because it can help get to the solution a little bit easier than just by going off of the units. For the majority of the last section of homework problems, 58 through 67, there are a lot of unit problems. You have to figure out how to get the units fixed in order to do the problem. But I was also able to use this formula. Okay, one last thing we talked about on Friday that I want to make sure to get up here as well. There are a bunch of conversions that are really helpful for the homework. Some definitions that are pretty helpful too. Start at the top. Miles into feet. All these, if you're at home and you forget one or need one, Google them. You have extra resources. If I hand you a weird homework problem that asks you about this many cubits per centimeter, Google those things. Use that to your advantage. Okay? You have these things available to you. Use it to find the conversion if you need them. Many of the problems that we have in these problems are similar to the chemistry problems, if you're in chemistry that you're going through right now, where it's a lot of unit conversion. If you are not great at the unit conversion, having a table like this is very helpful. Whenever I was taking a class like this, I always put it either at the very front or the very back, so I could always find it quickly and easily. I even at one point in time printed off an entire page of them, just so I had in my book. Okay? All right. Last thing I want to make sure to mention is that the homework uses a term, RPM. If you don't know it, it stands for revolutions per minute. It's revolutions on top and on bottom. Make sure you have those. Again, if it's a term you're not familiar with, if it's a term you're struggling with, you have resources outside this class. Don't expect me to answer every single piece that you might need. And don't delay doing a problem just because you don't know what this word means. Look it up. And bring it up in class, because if you miss something, then odds are somebody else probably did too. And maybe it turns out that you were able to find something they weren't. So, let's go ahead and look at the problems today. I want to get through as many as I can in the time we have. The vast majority of them are going to use multiple components off of this page. The two up here in red that are really important are the trig ones. There's one other trig one I'll put up here as well that we talked about previously. For revolutions, a single revolution is 2 pi radians. And a single revolution can also be equivalent to the circumference or the perimeter of whatever object you're dealing with. So those two are also very helpful. The final one I would put up here in blue is from previously in the class. To convert from degrees to radians and from radians to degrees. Whoa, weird, okay. Pi over 180. Remember, this is pi radians over 180 degrees. And the alternative version of that where it's 180 degrees over pi radians. Between all this information, we have all the pieces we need to do every problem in the homework in terms of the conversions itself. So, let's go ahead and pull up problem number 58. We'll work through as many problems as we got time for.
I think we did
58. You ready to do 58? Do we do 59 then?
Yeah.
All right. Let's do it. Okay. 58 and 59 are very similar, so even if we haven't done them, you still can get the information you need. All right, 59 in the homework assignment. A bicycle with 24-inch diameter wheels is traveling at 15 miles per hour. Find the angular speed of the wheels in radians per minute. How many revolutions per minute do the wheels make? So in unit conversion problems, which is the type of problems these are, it's important to note where you are at and where you are going. So in these problems, they will often try to tell you those things or give you clues to a formula you need to use. Like if it mentions angular speed, that would give us a formula we need to be using in order to do that problem. If it mentions something like linear speed, it gives us a formula to work with. If it mentions, like in this problem, radians per minute, it says find the angular speed in radians per minute. So it's giving us a closing point where we need to end up. So for our problem, let's notate the facts we have so far. We have a bicycle with 24-inch diameter wheels. That's a diameter. We have it's traveling at 15 miles per hour. I should point out here that if it's 15 miles per hour is defined as a linear speed. So in physics, this is always assumed to be a linear number. Angular speed should have an angle in it, like theta, like radian, like degree. That's how you can tell the difference between the two. Linear speed will typically have a distance of some kind instead. Alternatives, ones that are kind of in the middle, revolution per minute, is not really a linear speed, but it's also not really an angular speed. It's kind of in the middle. Okay? So, we have 15 miles per hour. What we're trying to get to, the end goal, is we're trying to somehow get this into radians per minute. Now to do this, I'm going to use this formula here. V equals omega r. Now remember, V is linear speed, omega stands for the angular speed, and r stands for the radius. So for this problem, I actually have 2 out of those 3, meaning it's a great place for us to start. Let's go ahead and do it. V. This problem, my V is 15 miles per hour. My omega is unknown. It's actually what I'm looking for. So I'm going to leave it over here as omega. My r, remember, is a radius. I'm not given the radius in the problem. But if we have our geometry big brains on, there's a way to convert a diameter into a radius. It's just half. So in this case, it would be 12. That's right. But keep in mind, it's 12 inches. That's really key here because in the problem, one side is in miles, one side is in inches. That's not good. And note what I'm looking for is radians per minute. So I need to convert every unit in this problem to somehow be in terms of either radians or minutes or in inches or miles. I need to make some conversions happen. So to start this problem, the first thing I'm going to do is I'm going to get my miles, I'm going to try to turn into inches. I'm also going to try to convert my hours into minutes, because that'll get me closer to what I'm looking for. So I want to convert hours into minutes. Now, if there is not a direct correlation, like a direct number value, like we don't have on our short list we had before a number that converts miles to inches, then see about getting closer. If I can't get from miles to inches, get from miles to feet. And then I can get from feet to inches. Okay? Use that conversion system to get to your numbers in case you don't have a bunch of them memorized. Especially if it's weird ones. Like if you ask me, how many seconds are in a day, I don't have that memorized. What I would do is I would use how many seconds are in an hour, how many hours are in a day. Get a way to get there rather than focusing upon getting there in one step. Try smaller, easier steps. So in this case, on the left-hand side, I have 15 miles per hour. I'm going to make some conversions. I want to end up with inches as part of it because I want to get them to cancel. And I want to end up with minutes as part of it. So let's make some changes. The miles, according to my cheat sheet, remember to get them to cancel, I have to have one on top and one on bottom. So I'm going to put a single mile on bottom and 5,280 feet on top. This will cause my miles to cancel, leaving me currently now as being feet on top, hours on bottom. So I'm a little closer. Let's do another one. I don't want feet, I want inches. So again, I have to have one on top, one on bottom. I have feet on top, so I have 1 foot now on bottom in exchange for 12 inches. So now if I do my canceling, mile is going to cancel with mile, feet's going to cancel with feet. I have inches on top and hours on bottom. I'm close. I've got one of these 2 done. Now I want to also get my hours into minutes. So I make my next change. Hours on bottom. So to get it to cancel, I put an hour on top, but for each hour there are 60 minutes.
Am I in?
Is it in?
Yeah.
It's been a Monday. Whew. Okay. So what let's do? Well, it'll cancel the hours with the hours, meaning I will have inches on top and minutes on bottom. And then I'll still have omega, which is the unknown, and 12 inches over here. So the left-hand side is now in terms of inches per minute, which is really close to what I want. The right-hand side has inches in it, so I can move it over and cancel when I'm ready. Before I do that, let's go ahead and fix some of this. So let's see. I'm going to use some fancy math tricks here. 15 and 60 cancel, leaving 4 behind. 12 and 4 cancel, leaving 3 behind. This becomes 3 times 5,280. So that would be 1,608. 1,5? Ah.
15840.
Thank you for checking my work. 1,508. 800?
840.
840. Thank you for checking my work. So we have 15840 inches per minute is equal to omega times 12. Now, it's an algebra problem. I have a variable times a number. I want to get the variable by itself. I divide to get rid of something that's multiplying. 12 times by 12 inches. Keep track of your units as you do this. It's a unit conversion problem, so you got to have your units everywhere you have them. 12 inches and 12 inches are going to cancel, leaving just omega. Now, a cool thing is going to happen here on the left-hand side. The inches and the inches are going to cancel, meaning on bottom, I still have minutes. But on top, so wait, hold on, let's divide that by 12 first. What is 15,840 divided by 12?
1,320.
1,320, thank you. So what happens to the top? We had inches, but we canceled it. This one's left behind. Normally, yes, right? Whenever you cancel something, there's usually one left behind, right? But there's a cool little factoid that I want to make sure is very clear here. If there's no units, it means that it's actually a radian. Radians are unitless. They have no inherent name because they're built by the device itself. They're defined by the circle, meaning that you don't need a unit for a radian. If you see a problem that has no units, like we talked about with angles, right? We said if it doesn't have a unit, we assume it is a radian. Here, if the units end up disappearing, we assume a radian was created when it happened. And this actually makes sense, because this is supposed to be an angular speed when we're done. How can you have an angular speed if you don't have an angle in it? So when the inches cancel, degrees appear. In this case, radians appear. So the question asks us to take this bicycle, find the angular speed of the wheels in radians per minute. This tells me we have a radians per minute of 1,320. And that is our solution. That was just the first piece. Now let's think of the second piece. Is pretty easy. It says, how many revolutions per minute do the wheels make? So, you are close, Giselle. You are very close. Yeah, I did. She said, I would just divide this by 360. She would be right in one case. If this was degrees. We don't have degrees. We have radians. So what we're going to do, we take this 1,320 radians per minute. We want to convert this into revolutions per minute. So we have to cancel the radians. Well, for each revolution, how many radians are there? So for each turn, how many radians are there? 2 pi. So the radians are going to cancel, leaving revolution on top and radian on bottom. Giselle, if this had been a degree problem, you would have been perfect and spot on. But it is a radian problem. So make sure to check that stuff. That's why we have that list of formulas up there, because it's really helpful. So, what's left behind? We have revolutions per minute. So we have 1320 on top divided by 2 pi. Let's see. So we would divide by 2. So 1320, so that'd be 660 divided by pi. Let's see. Somewhere around 210?
Yes.
What is it exactly, please? 2 decimal places.
0.08.
So, think about this. This sounds a little strange, but it actually checks out. 15 miles an hour is not that fast. But with a wheel that small, going 15 miles an hour means it spins 210 times a minute. So it's going fast. All right? Good sound effect, I know, right? So let's note some things we got to pick up that are really important here. First thing to pick up. If our distance ends up disappearing, it's a radian that's formed. Okay? If there's no unit, we assume it's a radian. Second thing, the conversion between radians and revolutions versus the conversion between radian or revolutions and degrees. You can use either one, just make sure you use the right one for the problem. This was number 59. Number 58 is very, very similar if you didn't get it already.
If someone needs 50, I have it written out in notes.
Thank you. Should we try number 60 next?
Yes.
In general, for these problems, the rule of the game is Find a way, we're probably going to be using this formula at some point in time, probably at the beginning. Find a way to get the units to match up to either what you're given or what you're looking for. And if the problem doesn't specify a unit, it's actually probably easier. Because the ones that specify units, we have to do a lot of conversions to, right? We have to convert this from miles per hour into radians per minute. So we have to do a bunch of different conversionary steps. The ones that don't have as many units are usually the easier ones because there's less converting that you have to do. Let's look at 69. Are we okay with what we have down for 59? Can I erase it? Okay. Let's go to 60. All right, so if I'm adding to my notes, anything that I would need, the big things to add would be the two things. If the units cancel, we're dealing with a radian. And those different little conversion pieces that we had on the previous page. How to convert between like a mile and a foot, or like a day and a year, or something like that. Okay, 60. A wheel of radius 8 inches is rotating at 15 degrees per second. So I'm going to stop right there and note what I got so far. I have a radius of 8 inches. It is rotating at 15 degrees per second. I can see that is a degree on top, which is an angle, and a second on bottom, that's a time. This tells me that 15 degrees per second, this is an angular speed. Now it's an angular speed in degrees, but it is an angular speed. Notice how I can interpret the information just using the units. That's a big detail that can be picked up from chemistry, from physics. You can interpret information just by looking at the units. All right, it says, what is the linear speed v, the angular speed in RPMs, and the angular speed in radians per second? If I'm honest with you, I hate this problem. For one reason only. Whenever they give you a problem like this, it looks like you're supposed to go in order. I think it is so hard to go in order on this problem. If I was doing this problem, I'd go in reverse order. Because the last thing is actually the easiest one to find. And is actually necessary to get to the other two answers. With the exception, you can go directly from where we started to the middle one, using what Giselle talked about. Using the degree instead. It can be done. Okay? And in fact, that's probably what I'll do for this problem, just to show it. Let's start off. I'm going to do the last part first. Just because it doesn't say to go in order, it just says do these three things. So it says, the angular speed in radians per second. Right now I have it in degrees per second, so I need to take the time, find a conversion that gets me from degrees to radians. So, my current omega is equal to 15 degrees per second. You notice that in many physics applications, and some chemistry applications, they leave seconds as an S. I try to write out second, so that way I don't think it's a 5. The number of times I have forgotten it's an S and thought it was a 5 and divided by 5, too many times. Okay, I don't want this. I want this to somehow become radians per second. Well, I've already got seconds, so that's a good start. I have to get rid of the degrees and turn it into a radian somehow. So my conversion, pi radians, 180 degrees. This will convert my degrees, will end up canceling on top and bottom, leaving just radians behind. And a second will still be there, so I know this is a good way to do this problem. Okay, so again, I can see the degree symbol here is going to cancel with the degree symbol there. Second is going to stay second. Radian is going to stay radian. This is looking good. There are two good versions of this answer. Let's show them both. The first version, without a calculator, would be 15 pi over 180. Or if you simplify, pi over 12 radians per second. Alternatively, if you have a calculator, you would probably want to convert this to a decimal. It's pretty nice. So that would be my next step. I'm going to convert this into a decimal of some kind. To convert it to a decimal, I just take pi and divide it by 12. It turns out pi divided by 12 is 0.2 6 something? 617? Beautiful. Radians per second.
That'd be 680.
Is this one 8? Okay. Thank you for correcting that. Beautiful. Okay. Third part's done.
Wait, so that's an answer?
Yep. Because the question says, and the angular speed in radians per second. This is now in radians per second. Both answers are actually good. Now, part 2 says to find it in revolutions per minute. I could either go from here and convert it to revolutions per minute, or I could go back to the beginning and convert it into revolutions per minute. Both should give the same solution. I'm going to showcase it by going with the degrees and converting it into revolutions per minute. Let's do it. So I have currently angular speed, 15 degrees per second. I'm going to convert this into revolutions per minute, RPMs. So first, I don't want seconds, I want minutes. So I do the conversion. There are 60 seconds for each minute. So the seconds will cancel, leaving just minutes on bottom. I'm halfway done. Part 2. I don't want degrees, I want revolutions. Thankfully, there is an easy combination. Each revolution is a very specific number of degrees. So, 1 revolution is equivalent to 360 degrees. So a single revolution can be written as 2 pi if you're already in radians. It can be written as 360 degrees if you're already in degrees. Use the one that's most beneficial to you. And keep in mind, I could also do this exact same problem from here. I would just have to do 0.2618 times 60 per minute. But because it's in radians, I'd have to then do 1 revolution is 2 pi radians. And it will eventually get the exact same results. Don't think it gets a different result, okay? Because that's how they're supposed to work. Now, if you use a decimal one, you'll probably get a decimal answer that's really, really close because you probably rounded at some point. This one should get you probably the exact answer if you do it right. Okay, let's fix this. So I take this 115 times 60 divided by 360. Ooh, I think this is 2.5. Revolutions per minute. So I can see seconds cancel, minutes left behind, degrees cancel, revolutions left behind, 2.5. So that answers part 2. They are easier if you know the conversions. If you don't know the conversions, these are almost impossible. Because you're going to be sitting there going, how the heck do I go from revolutions to degrees? What's that? I don't know. And you might as well be pulling numbers out of your butt. Right? Not a very comfortable place to have your hand. Well, some people. All right. 60. What is the linear speed? Now, at this point in time, I have to remember that to use these formulas, they need to be in radians. To use these formulas, it needs to be in a radian. So I'm going to use this number and this formula to get my solution. Ready? V is equal to omega times r. My omega is 0.2618 radians per second times r, which is 8 inches. So I multiply those two things together. Now remember, the radians is unitless, so it just disappears. It doesn't do anything. It's only there to remind us that it should be there. But radian times inches is just inches, because this radians are not even a unit. So I would get inches per second. And then I take 8 times 0.2618. 8 times 0.2618 would be 2.07. 2.09. And you might look at that and be like, that's a little weird. Inches per second is kind of weird. This problem didn't tell me to make it a certain way. It just said find the linear speed. I have done that. I could convert this into like miles per hour or feet per second. I could take the time to do that stuff, or I could not. The problem didn't specify a unit I needed to go into. It just said find the angular speed. So I'm going to stop right here with my 3 solutions. So this is part 1, find the linear speed, or linear velocity. This is part 2, asking us to find the revolutions per minute. This is part 3, asking us to find the radians per second. And again, if the problem asks me to go to a specific unit, then I will go to that specific unit. If it doesn't say, then I will stop whenever I feel like. That was number 60. And 61 is fairly similar. The difference being on 61, if you knew the radians per second, they want you to go find the degrees per second, so it's one minor difference. Similar formula stuff. Do we need to do 61 as well? Yeah? Okay. Let's do it. I'll do as many as I can. Alright. Am I good to erase this material? And I will do so. Alright, I'm going to boost up the speed a little bit. Since these are so similar, I want to focus instead upon getting the right values in the right spot, and let's see how we do with these formulas. It says we have a reel of radius 14 inches. 14 inches. We have a rotating at 0.5 radians per second. What does it say? What is the linear speed B, the angular speed in revolutions per minute, and the angular speed in degrees per second? Once again, I'm going to go in reverse order because I can. Okay, let's do it. Starting off with this one, 0.5 radians per second. It says I want it in degrees per second, so I need to convert the radians into degrees. How do I do that? For every 2 pi radians, got to make sure you put it in the right spot, 2 pi radians, there are 180 degrees. So, in theory, the radians cancel. I end up with 0.5 times 180 all over 2 pi. So let's see, that would be 90, so that would be 45 over pi, so that would be 14.67?
32.
14.32 degrees per second.
Wouldn't 2 pi be 360?
Ooh.
I was thinking about that.
Thank you. Good catch. So make sure always use the right conversion. If you use the wrong conversion, you will get the wrong solution. Thank you, Brian, for catching that, because I was totally going to miss that. Thank you, thank you, thank you. Okay, let's reset. The correct conversion is 180 over pi, not 180 over 2 pi. What am I thinking, Douglas? Okay, so now we do 0.5 times 180 over pi. Okay, so my correct solution should be 28.7?
28.64.
28.64 degrees per second. So note again, I have the original problem. I multiply by a specific fraction that's designed to put me in the correct format. I want radians per second to become degrees per second, so I multiply to change the degrees into radians or the radians into degrees. Okay, there's one solution down. At this point in time, I can actually go ahead and do the linear speed because I already have it in radians. So I could go ahead and do part 1, or I could do part 2. They're both going to be pretty similar. Let's do it. So, what is the linear speed V? V is equal to omega times R. Well, in this case, remember, the omega has to be the radian one. In order for these formulas to work, it has to be the radian one. So I'm going to use 0.5 radians per second times the radius, which in this case is 14 inches. Okay, 0.5 times 14 is 7. And this would be in inches per second. This would be my linear speed. Again, notice the radian disappears because it's unitless. We just have it there to remind us that it's there. So the inches stays on top, the second stays on bottom. 0.5 times 14 is 7. So 7 inches per second. Okay, so we've got the end, we've got the beginning, it's time to the middle. The middle part says we want to change this to revolutions per minute. Now I could use either one of these to find the revolutions per minute. I'm going to choose to use this one. It's going to get the same answer. Okay? It's going to get the same answer. So, to find revolutions per minute, I need to take 0.5 radians per second. I need to find a way to convert this into revolutions per minute. I'm going to get the easy one out of the way first. Converting seconds into minutes, there are 60 seconds for each minute. So the seconds are going to end up canceling. I now would have radians per minute. I don't want radians, I want revolutions. So I do my next conversion. For each revolution is 2 pi radians. So, if I've done this correctly, radian, second. What's left behind? I have a revolution on top, minute on bottom. That tells me I've probably done my math correctly as long as I didn't make a mistake with the numbers themselves, like what happened with the 2 pi. Those will be some of the most common mistakes, by the way, is just using the wrong conversions. Okay? Being like, instead of 5,280 feet per mile, you'd be like, I only did 1,280. You just use the wrong number. It happens. Okay, so I take 0.5 times 60 all over 2 pi. I'm feeling a number like 4.77.
Yeah.
Yes.
That's pretty good. So, that'd be 61.
Huh? We're in order?
When we come in tomorrow, we'll do 62 and 63 before lunch. If you want to see those, be here on time. We'll do the other 4 after lunch, or as many as we can get through. Giselle, any questions?
I have a question about Trig.
Oh, sure. I'm going to go ahead and stop this then. Bye, people. I don't care.